Hello everyone, I'm Qian from Tsinghua University, and today I'm excited to present our latest research on supervised large language model element for information retrieval via contrastive feedback. This presentation is focused on the elements of LLM capability with the needs of information retrieval applications. Large language models have shown remarkable capability, but one key issue is that their response often tend to be generic. This inability to capture the distinctiveness of each document, especially when dealing with similar input, limits their effectiveness in information retrieval tasks. Let's consider two representative application scenarios where large language models are used in information retrieval. These scenarios highlight the challenges and the need for more distinctive and context-specific response from large language models. In the context of information retrieval, documents often share a high degree of similarity. This inherent similarity makes it challenging for large language models to distinguish between them and provide specific response. The first large language model application in information retrieval is data augmentation for dense retrieval. Identical queries complicate the training of dense retrieval models. This is because they can lead to the false negative issue, which hinders the model's ability to learn effectively and provide accurate retrieval results. And the queries with specific information are expected in this scenario. In the second example of a large language model application in AIR is document summarization. When large language models generate identical summaries for different documents, it significantly reduces user efficiency for locating their desired documents, leading to a frustrating search experience. In information retrieval, it's crucial for large language models to generate a specific response that highlights the distinctions among similar documents. To address this challenge, we propose a novel method called reinforcement learning from contrastive feedback, or RLCF. Our proposed method, RLCF, uses a group-wise reciprocal rank to measure distinctiveness. Unlike previous alignment techniques such as RLHF, RLAF, and RLCD that compute reward scores in a point-wise manner, RLCF uses a group-wise reciprocal rank to assess response in a group-wise manner, which is essential for capturing the unique aspect of each response. We don't know the response is specific or not unless we compare with other documents. That's why we use the group-wide feedback for optimization in RLCF. And let's look at the overall framework of RLCF. It involves four main steps: identifying similar documents, generating response for these documents, calculating contrastive feedback, and optimizing the model based on this feedback. The first step in our framework is constructing a group of similar documents. This is done using a dense retrieval model that identifies documents with high similarity, forming the basis for generating distinct response. In the second step, each document in the identified group is fed to a large language model to generate response. This response will then be analyzed for their distinctiveness. And the third step involves calculating contrastive feedback using the group-wise reciprocal rank, or GRR. GRR reflects how distinctive the large language model generated responses are within a group of similar documents. From this equation, we can see that GRR is a variant of mean reciprocal rank. When the response is distinctive enough, the GRR score would close to 1, as the similarity of documents and its response is higher than others. The final step is to optimizing the large language model based on the contrastive feedback. We use the proximal policy optimization algorithm for this purpose, ensuring that the model learns to generate more distinctive and relevant response. And to evaluate our method, we conduct experiments on 3 representative tasks, including document summarization and document expansion for sparse retrieval and data augmentation for dense retrieval. These tasks help us to assess the effectiveness of LLM in AI scenarios. For the document summarization task, we utilize the LCS dataset for Chinese and GigaWord for English. We assess the performance using group-wise reciprocal rank and row-diff metrics. Row-diff measures the recall for distinctiveness words within a document among its similar document group, providing insight into the specificity of the summary. Additionally, we conduct a human evaluation to compare the performance of RLCF with both vanilla models and GPT-4. Here are the results for document summarization. Both RLAIF and RLCD are the point-wise alignment methods. They calculate the reward score only based on the response and the document itself, without considering other similar documents. The results indicate that the point-wise alignment methods have limited effectiveness in generating distinctive response and highlight the need for group-wise method. And this is the human evaluation result for RLCF. This result shows that RLCF optimized LLMs outperform vanilla LLMs in both English and Chinese summarization tasks. Given the massive scale of GPT-4, the effectiveness of RLCF is remarkable. And for the document expansion task, we used the bare dataset and evaluated the results using the NDCG at 10 metric. This task helps us assess how well RLCF can enhance the sparse retrieval models, and this is a representation tool in information retrieval. Here are the results for document expansion. The ILS metric represents the intra-list similarity, reflects how similar of the documents within the dataset. The higher the ILS means the higher similarity of the dataset and need more distinct response from large language models. Besides, we found that document expansion is more effective on the dataset with shorter documents. And from this table, we can see that LLM significantly enhances the effectiveness of document expansion on the suitable scenarios. We also evaluated RLCF in data augmentation for dense retrieval using the bare data set. The metrics used are NDCG at 10 and recall at 100. Here are the results of data augmentation for dense retrieval. From this table, we can see that LLCF has consistent improvement over all of the data sets in BR, where the improvement depends on the feature of the specific data set. We also conduct analysis on the parameter scales. The results show that LLCF consistently improves the performance across different parameter scales, highlighting its robustness. In terms of efficiency, LLCF proves to be more efficient compared to other methods like LAIF. The y-axis is the log scale of seconds. Therefore, the consumed time of LLCF for reward calculation is much lower than LAIF. And here are some cases for intuitively understand the effectiveness of LLCF. In case of data summarization, the response generated by vanilla large language models are identical. The LLCF optimized large language model could capture the distincts in the similar documents and generating specific summaries. And for query generation, in the first case, the query generated by vanilla large language models could even match all of the documents. And in the second and third cases, despite the generated query could be more irrelevant to the documents, they still lack specificity. Query generated by vanilla large language model for one document could still match another one. However, LLCF optimized large language model capture the distinctiveness of documents, providing specific and relevant summaries, thus improving the overall efficiency and effectiveness of AI systems. That's all. Thank you for your attention, and I'm happy to answer. Yeah. Thank you.